We'll go through our alcohol, amines, and actually we're going to touch on carboxylic acid nomenclature. Then we're going to go through and do substitution elimination reactions for alcohols, which ultimately just means kind of a review. We're not doing a whole lot of problems with them because we've seen them already to a much larger extent. So all the rules that applied that we talked about in Chapter 7 also apply to our substitution elimination reactions when we're looking at our alcohols. Okay? Please. So another thing before we even get into nomenclature was looking at some quick classifications. So we looked at carbocations. We say primary, secondary, tertiary, and we could rank them based on those. Alcohols and amines have a very similar system, except we won't look at anything as far as stability. We're just going to call them primary, secondary, or tertiary. Okay? And that will end up changing their reactivity. For instance, a primary alcohol, we might expect to react in what type of a substitution reaction? SN1 or SN2? 2, because we've got a primary substrate. Okay, so we got to go back to all of those rules and remember them again. So where are these terms coming from? When we take a look at our alcohols, evaluate the carbon where our alcohol is attached, so that OH. How many carbons are attached to that orange carbon? 1. If we go through, assuming I did this right, we take a look at the same thing for our secondary alcohol. How many carbons are attached to that center carbon? 2, kind of etc. all the way through with our tertiary. Where it gets particularly different is with the amines. Okay? The amines are going to refer to how many carbons are directly attached to the nitrogen. So in the case of a primary amine, how many carbons are attached to the nitrogen? 1. So we got a primary amine. When we move to the secondary, how many carbons? 2. Tertiary, 3. Okay? They all get called amines in those cases, and we rank, and like I said, the primary, secondary, tertiary phraseology is slightly different, okay, depending on what we're looking at. Kind of makes sense? Yeah.
Could a nitrogen have 4 carbons?
So, if you do remember, we could move to a nitrogen with 4 bonds. What's special about the nitrogen with 4 bonds? Positively charged. You got the right idea that it's charged. It's going to be positively charged. Okay, because in each of those other cases, the nitrogen has a lone pair. So there's 2 ways that we could remember that it was positively charged. What are those 2 ways? What was that? Okay, you had it memorized from the get-go. Okay, I went through and said what were the common charges for nitrogen, carbon, and oxygen. You needed to know those. Told you needed to have them memorized. They're coming back. Okay, so you need to be aware of them. So that's one way. The other way, you can count it out. Do your formal charge calculation. Nitrogen comes in with 5 valence electrons. So if we go through and do our formal charge calculation, formal charge is Fc. 5 valence minus the non-bonding electrons. How many non-bonding electrons are on that nitrogen? Do we see any? Nope. So we got 0 minus the number of bonds. 4. What do we get? Plus 1. Okay. So this nitrogen is possible. We can possibly get a 4-bonded nitrogen. What would we call that one? Anyone want to volunteer a guess? Butyrate. That's not a bad guess. Anybody know how to spell quaternary? Okay, there was enough people that sounded like they kind of knew. So we'll just say, there we go. Quaternary, saying we've got 4 different carbons on there. Okay, it can happen. It's usually fairly rare. I won't show you any cases, or you won't see any cases beyond this, I think. Okay. Other questions with the simple classifications? Okay. Now I'm pretty sure we move into our nomenclatures. Okay. So the next few sequences of slides are very information-packed. You've seen this kind of slide before. I'm pretty sure I went through and edited it this time instead of doing just the copy-paste. Okay. So we've got our priority of naming in the right-hand box. That is right-hand, yeah. Left-hand box in red. Our alcohols at this point are our highest priority. We looked at nomenclature for alkenes, alkynes, alkanes, and the alkyl halides. Okay, so our alcohols will be the highest priority. If we're going to go through and name a compound that has multiple functional groups, the alcohol takes priority. We'll see the all ending. Okay, and that's why we've got the ending here, that all ending. Okay, you'll notice I'm saying that substitutes for the E. Okay, it seems a bit odd to substitute it for the E, but what we're going to try and include in this is that if our structure is just single bonds, we can still include the information that it's all single bonds. So we could call it, for instance, let's go ahead and draw one out here real quickly. How many carbons? 4, so we would go with bute, right? You all remember that? Okay. We could go through and number our chain. Our alcohol is the only thing on there, so we could call this butol. Okay, but that doesn't give us as much information as we'd like out of it. Okay, we can add some information in the name by referring to the fact that all those carbons are singly bonded. Okay, so there's no other specific functional group. How would we include that? So let's say we ignored the alcohol, the OH. What would we call it? Butane, right? If we add the alcohol, what we're going to do is still include the fact that it is all singly bonded by including the AN for the ane ending, except we're going to substitute out the E for our all. And that's where we get butanol. Okay? So you guys see those individual substitutions and what's happening with the name. Okay, we will go through a couple examples. I just wanted a quick one there.
Do you have to do 1?
So should you put a 1 on there? Since numbering is never going to hurt, it's usually a good idea to include it just so that you don't forget it and leave it off when it's important. It's not important here because it's going to be by definition at position 1 unless otherwise specified. Okay, so we could call that 1-butanol. Questions about that one? Okay, you'll notice the nomenclature bulk rules are pretty much the same, kind of going through the general ideas. We just quickly did that with our butanol. We want to find our longest carbon chain. The carbon chain must contain the OH. Why does it have to contain the OH? Because the alcohol has the highest priority. So even if we get a longer carbon chain, if we count somewhere else, it has to include the alcohol. Okay, so make sure that's part of your name. We can then go through and add the information. So rule 3 is a little bit new and different than we've seen before. That's where we can add information about it being all single bonds. That's where we'll go with the an ending or an middle ending part. If it's got double bonds in it, we can include the ene. If it's got a triple bond in there, we can include the ein in the middle of the name. That will get definitely messy when you go through and name it. Okay, so let's go ahead and change our butanol into something a little bit messier. Let's do this. Okay, still 4 carbons, so we would go with, what's our name? Bute. What functional groups do we have? We have an ene. We do have the ane, but the ene will supersede, I guess, the ane name. So we can include the fact that we have a double bond in there. I'm going to need more space. Full address here in a second. Okay. And then we also have the alcohol. How does that change our name? We can have the all at the end. So we could go through and call it butanol, okay, with the ene in it as opposed to the ane. Okay, however, what's the problem with referring to it as just butenol? We need to know where each of those functional groups are. Okay, the alcohol, by definition, would be at position 1, so we don't have to specify it, but it's not a bad idea. So let's go ahead and include it in here. Okay, if I put the 1 way out front, what am I referring to? The ene or the all? I don't know. Okay, so what we've got to do is make sure that that 1 is more specific to the alcohol. We'll include it in the middle of that name. Okay, we have to include the hyphens because we have a number-letter transition. Okay, where's the double bond? Careful on how we number. We're going to number this direct. That was a bad way to draw an arrow. We're going to number right to left. 1, 2, 3, 4. Our double bond starts at position 2. So we will add our 2 in there to specify where the ene is. So we would get but 2 ene 1 all as far as the name goes, putting it all together. Okay? So when we start adding multiple functional groups, the name's going to get really messy to include all of those individual functional groups. Okay? Questions about how we put that one together? Questions?
Does it matter if you do EN versus ENE for the alkene?
I didn't look that one up. I'm pretty sure it should be just EN. Okay. It says EN or ENE?
EN.
Just EN? Okay. Yeah, I'm pretty sure when you do the alcohol ending, it's subbing for that last E part. Okay. It's again nomenclature, which is my weakest, but that's pretty sure going to apply. And same for an ine, if we made that a triple bond. Same idea. Okay? Questions about the alcohols, at least superficially? Okay? Just hearing some talking, no questions? It's just so boring and easy, right? You're talking about other stuff? Okay. So we could look at acids. I decided to do the acids next as opposed to the alcohol, or sorry, the amines, because the acids are very similar to our alcohol. Okay? If we happen to have an acid, we still have that OH, except now we've put that OH near another functional group, and we've now got the carboxylic acid. Okay? So instead of referring to that more complex functional group by its component pieces, the carbonyl and the alcohol, we put it together and we get a carboxylic acid. So one thing I want to address, which you can probably already see in the blue box there, is this is how you would see the line angle drawing for it, all the connections between the carbons, the oxygens, and the hydrogens. If we were really lazy and using a typewriter, okay, you would probably see it written as COOH. Yeah. It's where it originally came from. Okay? Because it's easier to type COOH into a straight line on a typewriter than it is to show all the bonds. Okay? So just kind of be aware of that. You will see that for sure show up in the textbook. Every question that I ask, unless I'm specifically testing you on that shorthand, I will show the connectivity. Okay? Showing all the double bond and the single bonds, all that fun stuff. Okay? Just want to make sure you're aware of that. As far as how we name that, acids have the absolute highest priority. Okay, so over every other functional group, its name is going to dominate our structure. Okay, so if we take a look, it was supposed to be highlighted in red, but at the very, very top, we've got acids. We'll change that E ending to an ic acid. Okay, same rules apply as we would get for the alcohols or anything else. So in rule 3, we'll still include that AN ending for alkanes, the EN for the alkenes, YN for the alkynes. Okay? Next kind of interesting piece of information that you may have noticed, particularly if you have the slides in, woo, I didn't mean to cross that out. I've added this hydroxy in parentheses. What happens if we've got a functional or a structure that has both an alcohol and a carboxylic acid? Sorry, I'm just drawing it like that for the moment. Okay, the carboxylic acid takes dominance or precedence over the alcohol. So the ending of our name, okay, what do we got? How many carbons do we have here? 1, 2, 3, 4, 5. The carbon in the carboxylic acid counts. It's part of that carbon chain. Okay, it's easy to lose it. So we'd be looking at pent. It's all single bonds, so we'd get the and we'd get our, now that I think about it, I think there's an O in there as well. Pentanoic acid. I don't think it's just ic. I think we have an O in there as well. Not positive on that either. Okay, so we get pentanoic acid, but we now have to specify where that alcohol is. Okay, and as far as I've told you so far with our alcohols, we change the E ending to all. There's no E ending in pentanoic acid. So we have to come up with a new way to refer to those higher order substituents beyond the alkanes and alkenes. That's where the hydroxy comes in. Okay, so we have that functional group, our OH there, is a hydroxy as well. Okay, so we can refer to this as a hydroxypentanoic acid. Where is the hydroxy? Position 4, we get 4-hydroxypentanoic acid. Again, this is going to be weak. I might be wrong on hydroxy. It might be hydroxyl. Usually substituent is YL. That was something I was writing it. I was going to check real quickly and I forgot. Okay, so just be aware of that when you look at your nomenclature. Okay, it's not something I'll grade you strictly on. As long as I get the idea, okay, that you're trying to name it hydroxy or hydrox, I'd probably even accept that. Okay, remember we're not super strict with nomenclature. Okay, that gets us our acids as far as functional groups. Okay, questions on naming those? Okay. The next one is going to be our amines. Okay, so we've got this highlighted in red. The amines are a little bit nicer because we can just refer to them as amines. Uh-oh. What are you saying? So with the amine nomenclature, same general idea. I've got this categorized slightly separately here, and I'm referring to it only or solely as the primary. So what we'll go through and do is name things as far as the primaries go kind of simply. So if we had this overall structure, what name would we give this guy? No, it's green. How many carbons do we have? 4. So we've got bute. Rule number 3. We've got the and. We can then go through and put in our last part. What? Dang it. Thought I caught all my copy-paste errors. Okay. And we get butanamine. Okay, so we kind of run it all together into one nice big name. Okay. Same idea with functional groups. We'd go through and specify where each of those were. To be extra nice or extra specific, we could call this 1-butanamine, but again, the 1 can be implied. Okay. Questions about the amines or other copy-paste typos? Okay, so I'm pretty sure our next slide goes to some examples before we make the amines more complicated. And I confused the computer, so let's go through a couple examples with this. Okay, let's pick the upper left as an example. First thing we want to do is what? Find the longest carbon chain that contains our highest priority functional group. Okay? So what's our longest carbon chain with the alcohol?
Oh, the alcohol.
So that's where this one gets weird, is how do we specify it? Okay? The alcohol is now kind of part of it. So the alcohol doesn't need to be at the end. It can be in the middle. Okay? So what we've got here is a 4-carbon chain. This is a little bit different than we've seen before, which I just now realized actually. So we've got 4 carbons, so we'll call it But-AN because they're all single bonds, followed by all for the alcohol. Where is the alcohol? Position 2. Because we don't have any other substituents, or like an ene or an ine to get in the way, we can call it 2-butanol. Sorry, butanol. The other option would be butan-2-ol. Why do we not call it 3? We want the lowest number to our highest priority group. Okay, so we're going to number right to left. 1, 2, 3, 4. Do we have any substituents on this structure? Yep, we have the methyl, so we could circle that, label that as our methyl. Where does the methyl show up? Position 3. So we've got as all together 3-methyl-2-butanol or 3-methyl-butan-2-ol. Okay, either of those names work. It ends up being whichever one you're more comfortable with. Okay? Questions about that one? Okay, so let's take a look at the primary amine now. We'll circle our longest carbon chain that contains our functional group. In this case, we've got how many carbons? 4, so we're looking at butanamine. I just ran it all together because I don't like nomenclature. We'll move through it faster. Do we have a substituent? Yes. It's a methyl located at what position? Why not 2? The amine is where I'm going to start my counting. 1, 2, 3, 4. Why start with the amine? Higher priority. So I get 3-methyl-butanamine or 3-methyl-1-butanamine. Okay? Questions about that one? Okay, one more short example before we hit a more complex one. Anybody know what the name of this compound is? Common name? Lower right-hand corner? Acetic acid. I think I heard someone say that. Okay. Also known as vinegar. That's not the IUPAC name. Okay, so that's just someone liked or found that group, called it an acetyl. Okay, that piece is commonly known as an acetyl group. If we add the OH to it, we now have an acid, so they called it acetic acid. Okay, not particularly an easy way to come up with it, so let's come up with the IUPAC name. What's the longest carbon chain? We got 2. I'm going to circle all of that because the carboxylic acid is part of the main chain. Okay? So with 2 carbons, I've got what name? F. Do I have any double bonds outside of the carboxylic acid functional group? No. So we're looking at F and if we go based off of what I've told you so far, change our ending to our ic acid, and we get ethanic acid. There's an O in there.
There is, yeah.
There's absolutely an O in there.
Ethanoic acid.
Okay. Questions about the acid? Okay. So
And there's no numbering for that because it's on one, right?
there's no numbering on that one because particularly with an ethyl group, or with 2 carbons, it doesn't matter which carbon I decide to put that functional group on, it will by definition be position 1. I can't possibly name it 2. Okay. If it was 3, yeah, even if we added a 3rd carbon on there, we did it straight off like that, made this a CH3, this was a CH2. We could still get away with calling it propanoic acid, okay, or 1-propanoic acid, or prop-1 or propan-1-ic acid, okay. So that 1 can pretty much slide almost anywhere as long as it's easy to tell that it's referring to the acid functional group, okay. So let's try and take a look at a trickier one. Because those were all too easy, right? Okay. Where should we start circling? On the acid side of this? Which direction do I go? Left or down? Why left? I have the amine. So it's 2 carbons either direction. The amine takes priority. I'm going to circle straight across. Okay, how many carbons do I have in my backbone? 6. So we've got hex. Do we have any double bonds or triple bonds? No, so we can go with hexan. We've got a carboxylic acid, so we can call it hexanoic acid. We then need to go through and identify our substituents. Okay, someone actually said the one I was going to end with, but that works. Whoops. Hydroxy, or eraser. Hydroxy or hydroxyl. I'll leave you guys to look that up. It's hydroxy. Someone look it. Okay. What's the easiest one to name? I would say the ethyl is the easiest to name down at the bottom. And then we've got the amine. Just like with the hydroxy, if we've got a higher priority group, we can't refer to it as an amine, so we come up with a new name with the amine being a substituent. That's where we get the amino. Okay, so that nitrogen at the end would be an amino. Okay, where do we start our numbering? On the acid carbon. So there's 1, 2, 3, 4, 5, 6. So we get 6 amino, 4 ethyl, 3 hydroxy. Hexanoic acid. 1 hexanoic acid. Okay? So it's ultimately the same rules. We're just adding new functional groups to kind of level up the difficulty. Okay? Questions about that? Okay, we will accept that and move on. One more issue is with these nitrogens. Okay? If we move to our secondary and tertiary nitrogens, those are going to become a bit more difficult to name. Where's our longest carbon chain that contains our nitrogen in the case of the secondary? I'm going to cross out the primary. What's our longest carbon chain for that one? It's really kind of weird. We could say, oh, there's a carbon over here, and then there's 2 more over here. Can't really say that's a chain, though, because the nitrogen broke up that chain. Okay? So we have to come up with a new nomenclature system. I don't know how to do it in advanced stages, so we'll only do simple ones. Okay, so we'll just deal with alkanes, alkenes, and our halides. We won't do anything above amines as far as difficulty for naming these. So what we're going to go through and do is use the amine name, but then everything attached to the nitrogen will now be a substituent on the nitrogen. Okay? So if we take a look at our secondary, whoops, we're going to start with nitrogen, so we'll start with amine. That is now my base name for this structure. What substituents are on the amine? We've got a group out here. So we got our blues. What's the easy one? The methyl. Okay. What's the other one? We could call it isopropyl. Are you all happy with isopropyl on that one? If you're not happy, speak now or forever hold your peace on that. Okay, isopropyl is what we'll stick with. As far as putting our name together, we want to do it in alphabetical order, and I'm pretty sure, but not positive, that the iso doesn't count. So we're comparing M to P. We'd get methyl isopropyl amine. Okay, remember alphabetical order I don't test you on. I just want to see that you're naming those pieces. Okay? Questions on putting that one together? You don't have to number it because they're all attached to the nitrogen. So it's an isopropyl functional group, which explains the piece on the left. That's directly attached to the nitrogen. The piece on the right, directly attached to the nitrogen. We don't have to do any special nomenclature or numbering systems after that. So we put our full name together. I would call this methyl isopropyl amine. Why the YLs? Think all the way back to our alkane nomenclature. When do we use YLs? When they're substituents. Okay. We're saying the isopropyl and the methyl are substituents on the nitrogen. Okay. So our nitrogen as a single atom counts as our main chain, if you will. Okay. Still no questions with isopropyl or anything about that name?
Is there a reason why we should have questions? Or?
If you aren't comfortable with isopropyl, we can call it by its IUPAC name. Okay, if you don't like numbers, you're not going to like it. We'll name the substituent according to the longest chain within the substituent, which in that case is an ethyl. That ethyl has a methyl substituent. So we have methyl ethyl. Where is the methyl? By definition, position 1, because that's where it attaches to the main chain. Isopropyl is also known as 1-methyl ethyl. Yes?
So if methyl was actually chloride, it would be chloride ethyl.
If we made that, and I can do that swap pretty easily here, instead of a methyl, I said that was a chlorine, we would then have 1-chloroethyl. Okay? Is the 1 necessary? 1's just like in any other situation can be assumed. So if we leave the 1 off, it is assumed the chlorine is at position 1. Okay, or the methyl's at position 1. It's a bit dicey when you start trying to name it out like that, but it works. Okay, we'll do the last one. Just decided we were done with that, by the way. That's why I'm erasing everything. Okay, so if we go through and take a look at that last one, what's our main chain? Kind of a trick question. Remember, we're dealing with the amines, so our main chain is the nitrogen. So our name for this is amine. Not a nice. One smile. One person's listening. Okay, do we have any substituents? We have a methyl, we have an ethyl, we have another methyl. Put it all together, and what do we get? Pretty close. We'll get ethyl dimethyl amine. Why the ethyl first? Alphabetical order, we don't count the Greek prefix. Okay? So we get ethyl dimethylamine. Each of those are substituents on our main chain being the nitrogen. Okay? Questions about that? Okay. Amine nomenclature for sure is in chapter 10. So there are practice problems within chapter 10 for the amine nomenclature. Okay? So now we can continue on to the fun stuff. Okay? We looked at this on Monday, kind of summarizing all the possible interactions that we could get with all these new functional groups. Okay? Of primary concern for this next section is looking at our alcohols, and in particular, we're going to be focused in on the electrophilic characteristics of our carbon and the nucleophilic characteristics of our oxygen. Okay? So those two are going to play a huge role in this. Okay? So, general substitution review. Okay? In theory, this is something you all have memorized or on note cards. So when you see an SN2 reaction, or you see the letters SN2, you immediately think of everything found within this column. Okay? That should be already in the back of your head. There shouldn't be any real thought about it. If I ask something about the substrate for SN2, you should immediately be able to tell me that we're looking at primary or zero areas reacting faster. And if I ask why, you should be able to tell me less steric hindrance or less size effects. Okay? If I ask SN2 and mention nucleophile, you should immediately tell me what about the nucleophile. It's strong. What would be the characteristic for a strong nucleophile? Lone pairs are definitely going to be there, but we'll take it a step further for a strong nucleophile. Charge, what charge? Negative. Okay? If we move over to the SN1, you should immediately be thinking tertiary substrates. Okay? Why tertiary substrates? They're more stable carbocations. Okay? How can we get stable carbocations? So we could look at size, we could look at electronegativity, or we could look at resonance. So resonance plays a huge role when we're looking at SN1 reactivity. Okay? So you need to be aware of these kind of extra little steps when you go through and process these problems. Okay? If you don't remember these, make sure it's on your cheat sheet for the exam and is very, very prominently featured so that if you suspect that you have a substitution reaction, you can immediately go to this and say, okay, these are the things that satisfied, this is the mechanism I'm running in. Okay? It can help you predict your products. So the first thing we're going to do is look at some misleading alcohol substitution reactions. First, we could start with the basics. Okay, what type of reaction occurred here? Substitution, good. Take it a step further. Which mechanism? SN2 because? Okay, how do you know you have a strong nucleophile? I don't see a super clear negative, so to explain that a little bit further. You're right. You're absolutely right. I agree with the strong nucleophile, but I don't see an obvious negative. I intentionally hit it. Why? What's the issue with that bond?
Ionic.
It's ionic. That metal and non-metal linkage separate into the ions. We're looking at I- and sodium plus. Those electrons spend all their time on the iodine. So we have a strong nucleophile. Whoops, let's try that again. So that's a good symbol for our SN2. What else could you look at? We have a primary alkyl halide. Primary alkyl halides are SN2. What else? No. You said it right, Becky. You'd have to know the structure of acetones. Let me add that in here. What can you tell me about acetone? It is polar aprotic, which favors which mechanism? SN2. So everything about this reaction screams SN2. So when you see it, you should immediately be saying, this is what's happening, I can propagate this through. What's the one complication that you should remember when you see that SN2? Particularly if you're asked to draw a product. Yes. Inversion of, that meant to be a capital T, whatever. Stereochemistry, I'm just going to erase it all anyway, right? Okay. Inversion of stereochemistry, which means if there is a stereocenter in the product, I need to be very, very careful with how it's labeled. Do I have a stereocenter in this product? No, so I don't have to worry about that. Okay? All of these things should be popping into your head within 5 to 10 seconds of looking at just the reaction. Okay? Very, very, very fast. Okay, I know. How do you get that to happen? Practice. Okay? That's why I'm trying to give you as many quizzes as I can. So we've got an SN2 reaction there. That one's ultimately review. Okay, so let's go ahead and try the next reaction. So when we take a look at this, what do you see? That wasn't a yawn, that was actually a primary, wasn't it? So primary, which means? What else can you tell me? We've got a negative iodine, which means strong nucleophile, which means SN2. Solvent, SN2. What would you predict for a product? And in this case, you'll notice, particularly in that first one, this is just for all of you that asked me to balance reactions. I did it. Okay? So let's go ahead and try and do this one balanced as well. So we propagate this out, what do we get? And okay. So we've got our substitution reaction. So everything on the surface of this looks good, except what's the answer? Nice and frustrating answer. No reaction occurs. Okay, so now that you know the answer, we got to come up with a reason why. Okay? Why would a reaction not occur? Kinda. Okay, why would iodine not be able to kick out this oxygen? That's one way to look at it. The way that I would look at it, because apparently I'm a sadist or masochist, whichever one it is, go back to the face test. If I take a look at that first reaction up at the top, look at my products, I look at an alkyl halide. Those probably aren't the nicest. I might cry, but it's not going to be that bad. And sodium chloride, if I cry, it's already on my face. So not that big of a deal. When I move to the next reaction, I get the alkyl halide again, so I cry. And strong base. So now I'm crying and melting. Okay? That's not particularly a good place to be. Chemistry's saying the same thing. OH minus, that species that has to leave this structure, is an awful leaving group. Why is that a terrible leaving group? We put a negative charge on an electronegative atom, but it's a small electronegative atom. It can't stabilize that electron density well enough to take the electrons entirely away. So what ends up happening, the hydroxide comes right back. Let's say we even form some of this. The hydroxide comes right back and kicks out the iodine. We'd rather have the negative charge sitting on the iodine than on the hydroxide. Okay? So we get no reaction. We get a major reaction going back towards our starting materials. That's an arrow. Jeez. Okay? So our primary concern here is that we have a bad leaving group. Okay? So what did we want to have in a good leaving group? What made a leaving group good?
Size.
Okay, what do you mean by size?
Able to hold
Able to hold
the electrons.
the electrons. So that's getting closer to what I want to see or hear. Okay? It's not just size. A leaving group needs to be able to do what?
Pull.
It's not even just pulling. It's a combination of all of these things. It needs to be able to stabilize the electrons it takes. Okay? So when we look at size, size is a grand thing because we can spread that negative charge over a large area. We could look at electronegativity because now that atom can hold the electrons. Okay? It just so happens that hydroxide is so small that it can't hold the electrons despite its electronegativity. Okay? So that's the issue. It likes to hold electrons, but it doesn't have the size to overcome it. And remember, size trumps electronegativity. Okay, so they compete with each other in a lot of cases. Size is our primary factor. Hydroxide is too small to stabilize the or the charge. Okay? So how could I stabilize that charge? What charge is it? It's a negative. So what do I need to give to a negative to make it neutral? What's the most available positive thing out there? A hydrogen atom. A metal is positive, but a metal is already there. That didn't work. We generate an ionic bond. We need a stronger bond between our negative and positive species. So what we're going to do is add a hydrogen to this reaction. Make sure I push the buttons in the right sequence here. So what we're going to do is instead of adding sodium iodide, where that sodium can't help the oxygen out, we're going to add HI. Okay? We are going to again go back and think phase tests. Alcohol versus HI. Which of those are you more concerned about? HI because it's a strong acid. What about that strong acid makes you nervous? The H plus. Okay? So what do I need to stabilize that H plus? A negative. Where do I have a negative? On the oxygen. So let's take the electrons on the oxygen and let's share them with the hydrogen. Okay, so we're starting a mechanism on this. We're going to share our electrons between oxygen and hydrogen, which means what have we formed? A bond. Which means how many bonds would be around that hydrogen? 2. Can we have 2 bonds to a hydrogen? No. So I can't draw a product of this yet because my product would have something that's invalid. Okay, so I have to go back to my starting area here and say I need to fix my arrows and adjust this so that hydrogen does not have 2 bonds. So what can I do? I can break a bond. Which bond do I break? The one between the hydrogen and the iodine. Where should those electrons go? Towards the iodine. Why? 2 big reasons. Okay, iodine is both bigger and more electronegative than hydrogen, so it can stabilize the electron density. What's the other big reason as far as the mechanism goes? How many electrons were around hydrogen? Okay, before we move those. Too many, which means where should the electrons go? They have to go away from the hydrogen. Our whole problem was that hydrogen had too many electrons around it. Okay, so we'll push those electrons towards the iodine. Ideally, we push them or drop that arrow directly on our iodine atom. Okay, what's the results of this now? Kind of close on the H2O statement. Sorry, I can't see what I'm drawing. We've got, whoops, it's not going to be enough space. Oh, it's not one thing, it's another, right? We got oxygen, hydrogen, hydrogen. There's our lone pair. What else is going on? We've got not technically iodine anymore. What do we have? Iodide, because it gained a pair of electrons. What else do we need to add? We need a negative charge on our iodine. Why? Gained electrons. What else do we need? Positive charge on the oxygen. Why? Shared electrons or lost electrons. What else do we need? Getting to the point where you need to be able to self-check. Is there anything else you need? No. Okay, so do we have a stable structure? No, why not? Okay, so we've got those charges. So what do we need to do? We need to somehow put them together. In general, we would say negative to positive. So we could have the iodine share its electrons with that positive charge, except how many electrons are around that positive charge right now? 8. Oxygen has its octet. So can iodine share electrons with the oxygen? No. That would exceed the octet of oxygen. So while the positive charge is usually a good way to identify an electrophile, that doesn't mean it is an electrophile. You have to evaluate its octet and determine, can it actually accept electrons? Okay, so the iodine cannot come in to stabilize that positive charge, which means I have to stabilize it by looking within the structure. So that oxygen, to stabilize the positive, needs to get electrons from somewhere within our compound. Okay. We can go to the carbon because the hydrogen is just as close. Why do we not go to the hydrogen? It's a pretty boring reaction. We just go backwards. Okay, so we'll pull our electrons from our carbon instead. What happens to the carbon? Our carbon should become positive. What kind of carbocation would I have? So if I attempted to draw this out, what kind of carbocation is that? Primary. Does that occur? No. So what does that mean we do? We bust out our pink pearl and we erase it. It is a pink pearl, right? The erasers, the pink erasers? Yeah. Okay, so we'll bust out the pink pearls and erase our answer. It's not good enough. Okay, we're generating something that's highly unstable. Okay, so we have to stabilize that positive as oxygen takes the electrons away. So that carbon is becoming very, very positive. So what can we do to stabilize it? We need to give it electrons. Where do we have electrons? We have the iodine. So the iodine brings its electrons in. What's the result? That looks pretty awful, but hopefully you can see it. Okay, if you're laughing that much, I'll fix it. Okay, we've got our iodine, and we've got H2O. What are we missing? Charges is a good thing to answer when I'm asking what are you missing. Is there any charge? No. The iodine started negative, but it shared its electrons, so it's now neutral. The oxygen started positive, but it gained electrons. It's now neutral. What have we now done? We've completed our substitution reaction. Which mechanism is this most like, SN1 or SN2? SN2. Which step is the SN2 mechanism, the first or the second? The second. Good call. What mechanism is the first one? I might have heard it there. Let me write SN2 first. Anybody else think of an idea on what that step is? What happened in the first step? You changed the location of a hydrogen atom acid base. Reduction requires 2. Okay, so we've got an acid-base reaction in our first step. Okay, so when we go through and do our substitution reactions, we have to remember the acid-base stuff that we talked about on Monday. We need that good leaving group. We must have the alcohol act as a base first, pick up that hydrogen, generate the good leaving group so that it can then leave and produce our product. Okay? So the next slide summarizes everything right there. Okay? When we go through and look at our overall substitution reactions, our alcohols are terrible leaving groups. Okay? We generate that hydroxide. So to get the substitution reaction to occur, to get the nucleophile to attack and kick out that OH, we have to make it better. So what we have to do is run through what we could refer to as an activation step to increase the electrophilicity of the carbon. Okay, so that a nucleophile can actually come in and attack. Okay, so we must do an acid-base activation step first. Okay, so we have to remember back our good leaving groups. Okay, our good leaving group needs to be able to stabilize the electrons that it's taking with it. Okay, so halides were great because they were big and electronegative. Hydroxide is just electronegative. Okay. It needs to have that size effect as well to be able to take the electrons nicely. Okay? Questions? Okay. So nomenclature definitely took more time than I thought. There are some other substitution reagents or reactions that we can run. So that first one is now the standard. That's kind of a repeat for us. Okay? The next 2 substitution reactions are a little bit new for us. Okay, and by a little bit new, I mean they're actually really new. Okay, we haven't seen them at all yet. Okay, so let's take a look at the second one. What's different between our first and second reaction? Okay, we're looking at a weird new species here. Okay, that weird new species does supply chloride. Okay, so that could be where our chloride's coming from. What else does it supply? Okay, oxygen and sulfur, which that's not super exciting. So let's evaluate each of those a little bit closer. What partial charge do you think the chlorides would be? Partially negative because they're more electronegative than the sulfur. Okay, so that makes sense. So I would expect my chloride to be partially negative on each of those. My sulfur is partially positive from one of those, partially positive from the other one. So if we average that, what do we get? A larger partial positive. Okay? What else do we see in that structure? Say at the top of it. We have an oxygen. What do we know about oxygen? It's electronegative, meaning it's partially negative. What does that mean the sulfur then becomes? Partially positive. So we get 3 groups all converging on the same atom, making that sulfur atom ridiculously partially positive. Okay? So sulfur on its own wouldn't be super positive, but if I attach some electronegative elements to it, I can make it positive. Much the same way that hydrogen on its own isn't particularly positive. Okay, a hydrogen atom. So what do? I attach an electronegative element next to it. That takes the electrons away, making that hydrogen very, very positive. So it's effectively the same thing, but because we're moving further through the periodic table with a sulfur, we have to add more electronegative atoms to it to really help make that more and more positive. Okay? So we're going to end up going through a very loosely pseudo-similar mechanism. Okay? With our sulfur being positive, what do we need to stabilize it? A negative, which means where do we find our negative? On our oxygen. Sulfur would then have too many electrons around it. This is going to be a very fast mechanism here. I'll show you a better one in just a second. So we could break the easiest bond first, which would be that pi bond. Okay? We now have increased the issue drastically because our sulfur now has 4 electronegative elements attached to it. So it gets irritated and grabs electrons back from something. It'll grab them back from that same oxygen that we broke. But now we have too many electrons around it. It kicks out the chloride. And like I said, this is a very fast and loose mechanism. Kicks out the chloride, which then goes and substitutes at our carbon. Okay, which then breaks that bond over to there too, which we could just kind of push all the way through. Okay? Like I said, very, very fast. We'll stepwise that in just a second. The net result is that per alcohol, okay, we can kick off a single chloride. That gets us one of these alkyl chlorides. But then we don't have this species. And we don't have this species. So what ends up happening, the leftover piece reacts with another alcohol. So if we were going to balance this, we have to put 2 times in front of our alcohol and 2 times in front of the chloride. So the species in the middle, okay, our sulfur oxide chloride species there, will react with 2 alcohols. It's got 2 reactive chlorides. It can exchange those in this reaction. Okay? I will show that mechanism a little bit slower in just a second. Okay? So, probably the best way to remember that is just the results. If you see that species with alcohol, what happens? What's the product of that reaction? What occurred? Let's look at the organic material, because we're looking at organic class. What happened to our organic compound? An OH was replaced or substituted with a chloride. What kind of reaction do we do here? We have a substitution reaction. Okay? So if for some reason we didn't want to do the acid reaction, we could go through and use this species, also known as thionyl chloride, to do the substitution instead. Okay? The last reaction on there is also a substitution. It's a little bit different because we're going to start off with a strong base. So what's the reactive species in that case? Take a look at that compound, NaH. Be a little bit more specific with it. What charge is that hydrogen? Hydrogen is typically positive because it's attached to an electronegative element. Are metals electronegative? Hydrogen will take the electrons away from the sodium, and we get Na plus and H minus. Okay? This species, for reasons we'll talk about next month, or probably in a lecture that I'll post this weekend, acts solely as a strong base. It's not a good nucleophile. Okay, so it needs an acidic hydrogen. Where is there an acidic hydrogen? On our alcohol where? I don't want you to say on the leaving group. Try that again. Where's the acidic hydrogen? What atom is it attached to? It's attached to the oxygen. So what ends up happening? Our hydride comes along, pulls the hydrogen off as H+, and it puts electron density on that oxygen. So much electron density that what charge does our oxygen become? It becomes negatively charged. What can you tell me about that negatively charged oxygen? It can now act as a nucleophile. So if we go through and evaluate the second step of this reaction, what do I need to stabilize that negative? A positive. What's positive in that second step? The carbon right there. I can get what type of reaction? A substitution. Which type of mechanism? SN2 because strong nucleophile and the substrate structure is primary. Okay. I think I just barely have enough time to go through and do the thionyl chloride reaction. Can't quite decide if I just want to tell you to memorize it or not. So thionyl chloride has an extra little added bonus to it. So if we go through and take a look at that first reaction there, okay, when you go across, we do the substitution reaction, so immediately you should have that, not immediately now, but immediately eventually. You'll have the reagent memorized. You see thionyl chloride, so SOCl2, and an alcohol means you do a substitution reaction. The alcohol is pulled off, the chloride's put on. Okay, so when you look at that first reaction, that should be it. You're happy with that answer. When we look at the next reaction down, if I asked you to predict the product, so let's pretend we don't see that. Okay, we'll go through the same logic. Okay, thionyl chloride, alcohol, what should my product be? Substitution, I should have the chloride there. But now you should mildly panic, because you go back and look at the starting material, and what do you see? A wedge, which means stereochemistry is important. Okay? Thionyl chloride goes through a slightly different mechanism than we've seen before, so it's not one that I expect you to know, but I expect you to know the result. The result is that the chloride substitutes from the exact same side. So if I start with a wedged alcohol, my product will be a wedged chloride. Okay, I'm going to attempt to draw this in the last 3 minutes. Okay? So you will need to know that extra piece of information with the thionyl chloride. Okay? That will be one of the second tier level of questions. You should be able to at very least get me to the secondary chloride. Hopefully you would then know the stereochemistry. That would be an added level of points. Okay, does that make sense? At least as far as question asking. Okay, so let me draw out the, what do I want? This. Come on. Okay, maybe I can't draw out the mechanism. Got it? Okay, so we'll start with our secondary alcohol. We've got our thionyl chloride. Our lone pairs on our oxygen. Can you guys see that? Chloride, the oxygen comes in, attacks the sulfur. Okay, the sulfur has now too many electrons around it. So we'll push the electrons onto the oxygen. Okay, we'll break the pi bond first, not the chloride bond. Why? It's pi bond versus sigma bond. So the pi bond makes more sense to break. Sorry, I'm about to switch colors into black. I like black better in this case. We draw out our structure. We've got our wedged oxygen. Got our sulfur. There's our chloride. Our negative oxygen and our other chloride. Okay. That sulfur now has 4 electronegative groups attached to it. It doesn't like that. So what it does, we'll grab the electrons back from our negative oxygen. Why would it grab them from the negative oxygen? Because why? Sorry. It's negative, so it's the most reactive oxygen in there, the most likely to donate its electrons. The chlorides don't want a second bond. The other oxygen already is low on electron density. But now the sulfur has too many bonds, so it now has to break a bond. What bond does it decide to break? It'll break the chloride. The chloride bond breaks, goes to the carbon, but now the carbon has too many electrons, so it kicks the electrons out onto the oxygen. Our result and ta-da! Okay. If we take a look at our sulfur, it looks like a 5-year-old drew that. If we take a look at the sulfur is still there are some very talented 5-year-olds apparently, clearly, right? The sulfur is still very, very positive because it has 2 electronegative elements attached to it in the oxygens, and it still has that chloride attached to it. Okay? It can react a second time with another alcohol. After that reaction, we generate a very unstable species, and that decomposes to form the SO2 and the HCl. Okay, and that's where those 2 pieces come from. It's ultimately our sulfur, our thionyl chloride, decomposing at a later stage. Okay? Questions about that? Good. If you got questions, come up here. Otherwise, you're done.
What is the